the universe. It's vast, mysterious, and ever-expanding, a cosmic ocean of stars, galaxies, and planets stretching out in every direction. But have you ever wondered, does this ocean have a shore? Does the universe have an edge? Or does it go on forever? It's a question that has captivated astronomers, physicists, and philosophers for centuries. For millennia, we gazed up at the night sky and pondered our place within it, wondering if the stars we see represent a finite tapestry or an infinite canvas. Today we stand on the precipice of discovery, armed with powerful telescopes and sophisticated theories that allow us to peer deeper into the cosmos than ever before. So, let's embark on a journey to the edge of what we know and explore what scientists think about the true nature of the universe and its ultimate fate. Imagine yourself standing on a tiny speck of dust, surrounded by a vast, dark sphere. You can see as far as your eyes allow, but you know there's more beyond the horizon. This sphere, my friends, represents the observable universe. It's the portion of the cosmos that we can see from Earth, the light that has had enough time to reach us since the Big Bang, roughly 13.8 billion years ago. Now, the observable universe is mind-bogglingly large. We're talking about a diameter of about 93 billion light-years. To put that in perspective, 1 light-year is the distance light travels in a year, a staggering 5.88 trillion miles. So, 93 billion light-years is a distance so vast it's almost impossible to comprehend. But here's the catch, the observable universe is not necessarily the entire universe, it's just the part we can see right now. Think of it like this, imagine you're standing on the deck of a ship in the middle of the ocean. You can see a certain distance around you, that's your observable horizon. But you know that the ocean extends far beyond what you can see. The same goes for the universe. Just because we can't see beyond the observable universe doesn't mean there's nothing out there. In fact, many scientists believe the universe is much larger than what we can observe, perhaps even infinite. How can this be? Well, imagine for a moment that the universe isn't static, like the surface of a calm pond. Instead, picture it as a constantly expanding balloon. As the balloon inflates, the points on its surface, representing galaxies, move farther apart. Now imagine you're an ant on that expanding balloon. You can only see a certain distance around you on the balloon's surface, but as the balloon inflates, points beyond your observable horizon eventually come into view. The universe might be behaving in a similar way. As it expands, regions that were once beyond our observable universe gradually come into view. This means the observable universe is constantly growing, but it's always just a tiny fraction of the whole. So, the next time you gaze up at the night sky, remember that you're only seeing a tiny sliver of the cosmic pie. There's a whole universe out there beyond what we can see, waiting to be explored. In the 1920s, a revolutionary discovery shook the foundations of astronomy. Edwin Hubble, an American astronomer using the powerful Hooker telescope at Mount Wilson Observatory, observed something astonishing. He was studying distant galaxies, those swirling islands of stars scattered throughout the cosmos, and he noticed something peculiar about their light. Hubble found that the light from these distant galaxies was stretched, its wavelength lengthened, shifting towards the red end of the spectrum. This phenomenon, known as redshift, is analogous to the Doppler effect we experience with sound waves. Think about an ambulance siren. As it approaches, the sound waves are compressed, making the pitch higher. As it moves away, the waves stretch out, lowering the pitch. Hubble observed that the farther away a galaxy was from us, the more its light was redshifted. This implied that these galaxies were moving away from us, and the farther ones were receding faster. This groundbreaking discovery led to a profound realization. The universe was not static and unchanging, as previously thought, but it was expanding. Imagine a loaf of raisin bread dough rising in the oven. As the dough expands, the raisins embedded within it, representing galaxies, move farther apart from each other. This is similar to what's happening in the universe. Space itself is expanding, carrying galaxies along for the ride. But what does this expansion mean for the fate of the universe? Will it continue to expand forever, or will it eventually slow down, stop, and perhaps even reverse course? The answer, my friends, lies in the battle between two fundamental forces, gravity and the mysterious force driving the expansion, which scientists have dubbed dark energy. Gravity, as we know, is the force that attracts objects with mass towards each other. It's what keeps us grounded on Earth, what holds the moon in orbit around our planet, and what binds galaxies together in clusters. In the context of the universe, Gravity acts as a brake on expansion. The gravitational pull of all the matter in the universe tries to pull everything back together, slowing down the expansion rate. However, observations have shown that the expansion of the universe is not slowing down. In fact, it's accelerating. This discovery, which earned the 2011 Nobel Prize in Physics, took the scientific community by surprise. It means that there's something else out there, something we can't see or fully understand, counteracting gravity and pushing everything apart. This mysterious force, dubbed dark energy, is thought to permeate all of space, acting like an anti-gravity that drives the accelerated expansion of the universe. We know very little about dark energy, what it is, or where it comes from, but its presence has profound implications for the ultimate fate of the universe. Chapter 3. The fate of the universe, the grand finale of the cosmic play, is a subject of intense speculation and debate among scientists. Will the universe continue its relentless expansion, or will it eventually succumb to the pull of gravity? Will it end with a bang, a whimper, or something in between? Let's delve into three main theories that attempt to answer this profound question: the Big Freeze, the Big Crunch, and the Big Rip. First, we have the Big Freeze, also known as the heat death of the universe. This theory suggests that the universe will continue expanding indefinitely, driven by the ever-present force of dark energy. As the universe expands, galaxies will drift farther apart, and the space between them will become colder and emptier. Stars, those fiery furnaces of the cosmos, will eventually exhaust their nuclear fuel and die out, leaving behind remnants like white dwarfs, neutron stars, and black holes. Over vast stretches of time, even these remnants will decay and evaporate, leaving the universe a cold, dark, and desolate place. In this scenario, the universe doesn't end with a cataclysmic event, but rather a slow, gradual decline into a state of maximum entropy, where everything is evenly distributed and no more energy is available to do any work. Next, we have the Big Crunch, a theory that was once the leading contender for the end of the universe. In this scenario, the expansion of the universe eventually slows down due to the gravitational pull of all the matter within it. Like a ball thrown upwards that eventually succumbs to gravity and falls back down, the universe, in this model, would begin to contract. Galaxies would rush towards each other, colliding and merging as the universe gets smaller and hotter. Eventually, everything would collapse into a single, infinitely dense point, a singularity mirroring the Big Bang in reverse. This cosmic implosion would mark the end of space, time, and everything in it. Finally, we have the Big Rip, a relatively new and more radical theory. This scenario posits that the expansion of the universe, driven by dark energy, will continue to accelerate at an ever-increasing rate. As this acceleration intensifies, it will eventually overcome all other forces in the universe, including gravity and the forces holding matter together. Galaxies will be torn apart, stars will be ripped from their orbits, and even planets will be shredded into their constituent atoms. Ultimately, the very fabric of space-time itself will be ripped apart, leaving behind a chaotic and utterly unrecognizable state. So, which of these scenarios is the most likely? The answer, my friends, is that we don't know for sure. The fate of the universe hinges on the properties of dark energy, a force we still don't fully understand. Chapter 4. The concept of infinity is one that has challenged and fascinated mathematicians, philosophers, and astronomers for millennia. It represents a realm beyond measure, a boundless expanse that defies our finite minds. But what if I told you that the universe itself might be infinite? The idea of an infinite universe, a cosmos without edges or boundaries, is a truly mind-boggling concept. It means that there would be no center of the universe, no single point from which everything expands. Every point in space could be considered the center, with an infinite expanse extending in all directions. To grasp the concept of an infinite universe, we need to think beyond our everyday experience of space. We're used to thinking of space as flat and Euclidean, a three-dimensional grid where parallel lines never meet. But Einstein's theory of general relativity, which describes the nature of gravity, tells us that space is not flat, but curved. Imagine a flat sheet of paper representing a two-dimensional universe. If you draw two parallel lines on this sheet, they will indeed remain parallel forever. But now, imagine curving that sheet of paper into a sphere. Now those same parallel lines will eventually intersect at the poles. This curvature is caused by the presence of mass and energy, which warp the fabric of spacetime around them. Similarly, the universe itself could be curved not just in the three spatial dimensions we perceive, but also in a higher dimension that we can't directly observe. One possibility is that the universe is shaped like a sphere, a three-dimensional analog of the curved surface of a ball. In this model, if you were to travel in a straight line for a long enough time, you would eventually end up back where you started, much like circumnavigating the globe. Another possibility is that the universe is flat but infinite, stretching out endlessly in all directions. This would mean that there are infinitely many galaxies, stars, and planets out there, many of which may be similar to our own. The idea of an infinite universe also raises intriguing questions about the nature of reality. If the universe is infinite, does that mean there are infinitely many copies of ourselves out there? Could there be other universes, perhaps with different laws of physics or different versions of ourselves? These are questions that currently lie beyond the realm of scientific inquiry, but they highlight the profound implications of contemplating an infinite cosmos. Chapter 5. So, after our journey to the edge of the cosmos, what can we say about the question that started us on this adventure? Does the universe have an end? The truth is, my friends, we still don't have a definitive answer. The fate of the universe remains one of the most profound mysteries in science, a question that continues to drive research and inspire awe. The answer, as we've seen, depends on several factors, most importantly the nature of dark energy. If dark energy continues to drive the accelerated expansion of the universe, then the big freeze or the big rip scenarios become more likely. However, if dark energy weakens or changes over time, or if there's some other force at play that we're not yet aware of, then the big crunch or some other unknown fate might await us. Scientists are actively pursuing these questions, using powerful telescopes and sophisticated computer simulations to probe the nature of dark energy, the geometry of the universe, and the distribution of matter within it. They're looking for clues in the cosmic microwave background radiation, the faint afterglow of the Big Bang, which provides a snapshot of the early universe. They're studying the large-scale structure of the universe, mapping the distribution of galaxies and galaxy clusters to understand how gravity has shaped the cosmos over billions of years. And they're developing new theoretical models, pushing the boundaries of physics to explain the observed properties of the universe and make predictions about its ultimate fate. The quest to understand the universe and its ultimate fate is a journey without a known destination, but it's a journey filled with wonder, discovery, and the pursuit of knowledge that defines our species. So, let's continue to explore, to question, and to marvel at the vast and mysterious cosmos we call home. As we've explored, the question of whether the universe has an end is a profound one, and the answer remains elusive. The universe is a vast, mysterious place, and we are still piecing together its secrets. But that's the beauty of science. It's a journey of constant discovery. Every new observation, every new theory, brings us one step closer to understanding the cosmos and our place within it. So keep looking up at the night sky, keep asking questions, and never stop exploring the wonders of the universe.